slideshow? Okay. Yeah. Yeah.
The next speaker is Owen from Cornell. He's speaking on practical distance computation in the space of phylogenetic trees.
Okay, so I'm actually talking about the same problem as the previous speaker, but I have a slightly different approach, so it should hopefully still be interesting. So I'm computing geodesic distance between two trees, as introduced by Bellera, Holmes, and Wagman. Yeah, and so they constructed the space of trees, right? So they constructed for n taxa, they constructed a space that has all trees, rooted trees with n leaves in it. And so we're allowing degenerate trees in, because you can just think of them as having some of the branches having length 0. And I'm only going to consider lengths on the interior edges because, so in the actual distance, you would do a computation with the lengths on the edges going to the leaves, but it doesn't make the problem any more mathematically interesting. Okay, and so we're using the standard definition of an edge, that of a bipartition. And two edges are going to be compatible. You might recall if they exist in the same tree. And we can check that by just mathematically or algorithmically by just checking if one of 4 intersections is empty. Okay, and so I'm going to have sequences of trees. And so to change between two trees, I have this one move in which we drop some edges and then we add some edges. And so when you think of dropping an edge, I'm thinking also of just shrinking that branch length to 0 and then growing it out, say, a new edge. And so we don't need to grow it, we don't need to add as many edges as we dropped, for example, and we can get a degenerate tree. Okay, and so minimal change is a rotation, right? Because we just drop one edge and then we can grow out a new edge in either of two ways. Okay, so each of the trees, so each topologically different tree is going to get its own orthant. An orthant is the n-dimensional version of a quadrant or an octant. And so we're going to do this by, for each interior edge, we're going to assign it to an axis or a dimension. And then the exact length of those edges are going to be which coordinate that particular tree occupies. So if we have a tree that's the same topologically, but with different interior lengths, then it's just a different point in that same orthant. And then if the tree has one of the branch lengths is 0, it's going to be on the axis or the boundary of the orthants, which is then how we connect them, right? Because both of these trees, if we shrink either E2 or E3 to 0, we get that same boundary tree. And so it makes sense to glue those two orthants together along that boundary. And so in general, the tree space is pretty complicated. This is another picture of the structure of the space of trees with 4 leaves. And it looks like the Peterson graph, where each of the edges is actually a quadrant, and then the points are those axes. And so it's piecewise Euclidean, but as you can see, it's not a Euclidean space. And then the geodesic distance is simply the shortest path between the two trees in this space, or the geodesic between them. Right? And then, as I mentioned, right, there's always the cone path between the two trees, in which you just go straight to the origin and then back out to your target tree. Okay, and so one of the nice properties of this space that was proved in the original paper is that it's cat 0. And that means that it's got unique geodesics. So there's a unique shortest path between the two trees. And so this is one reason you might be interested in this distance, because there's a unique shortest path. So there's a unique point halfway along that path, and that could be considered in some ways an average of the trees. And you can also extend that definition to define a centroid, which was done in the original paper. Okay, so what I'm looking at, so my ultimate goal is to find an efficient algorithm. It's an open question whether this problem, whether you can compute this distance in polynomial time or not. And for the rest of this talk, I'm going to assume the trees don't have any shared edges, because if they do, we can just decompose the problem into 2 smaller ones. And we can do that in polynomial time. Okay, so I'm going to introduce this notion of path space. So basically so we can get, if we have a target tree, or sorry, a starting tree and target tree, we can get a sequence of trees going between them, right, by dropping an edge, adding an edge. So that will give me my first tree, and then I can do the same to get another tree. And then finally, if I drop E2 and add F1, I get my target tree. Sorry, add F2, I get my target tree. But that's not the only way I could get between those two trees, right? I could also have dropped, say, E2 and E3 and added F3, drop the remaining edge, add the remaining edges. And you can imagine there's a whole bunch more of these as well. And I should just point out that, so at each step, I'm only dropping edges that were in my original tree, and I'm only adding edges that are in my target tree. So I'm not going out of my way and adding extra edges, or dropping edges I just added, or things like that. Okay, and so for any one of these sequences, right, so each of these trees, it corresponds to an orthant, right? The orthant containing all trees with that topology. The first tree corresponds to that orthant. Second, so it's degenerate, right? So it corresponds to a two-dimensional orthant. Third one to that one. And so the union of those orthants is what I'm going to call a path space. Okay. So in the original paper, Belair, Holmes, and Wagman showed that the geodesic, or shortest path between these two trees, is contained in a path space, although they didn't use that terminology. Okay. So my plan for the algorithm is to consider all maximal path spaces, where a maximal path space is what you might think in that it contains other path spaces, but is not itself contained in a path space. So I'm going to find a way to represent them all very nicely. Then I'm going to show for any maximal path space how to compute the shortest path between the two trees just within that path space. And then I'm going to put the two together using dynamic programming. Okay. So intuitively, right, we want, for maximum path spaces, we want the orthants to be as large as possible or have as high dimension as possible, which means that the trees they correspond to should be containing as many edges as possible, right? Because each edge gives you an extra dimension. And so we want to, at each step, be dropping as few edges as possible, adding as many edges as possible, and again, this condition that we shouldn't be going out of our way and adding extra edges. Okay, so we can define something called the partition poset, or partially ordered set, on the two trees. And what we're going to do is look at which edges are incompatible with which edges in the other tree. So we look at which edges in the target tree are incompatible with edges in the first tree, right? Because these are edges that can't exist in the same tree. Okay. And then we can just we can represent all this notation in a partially ordered set, in which the elements are the edges in the target tree, and they're ordered by inclusion on the edges they cross or are incompatible with. And then, so this relates back to maximal path spaces in that we can prove that a path space is maximal if and only if what we want to do is add in one of those, our first transition is going to be to drop one of the edges in the minimal element, drop the edge associated with a minimal element and bring in that minimal element, right? Because then we're dropping as few edges as possible in order to bring in an edge. Okay. And we can further introduce this idea of a closure. And what it is if we have a set of edges in our target tree, the closure of that set is going to be, so all those edges are incompatible with some edges in our starting tree, right? So we drop all the edges in the starting tree that they're incompatible with, so we can bring in the set of edges A. But then we actually might be able to bring in some extra edges that aren't in A. And so that set of all the edges we can bring in as the closure of A. And so in this example for this poset, the closure of F1 is F1, closure of F3 is F3, but the closure of F2 is actually F1, F2, and F3, because to bring in F2 we have to drop all the E edges, and then we can just bring in all the F edges. Okay. And so this gives us a way to construct something called the path poset. And so what we do is we start at the root, and then I'm going to pick a minimal element to bring in. So let's say I pick F3. So I'm going to drop E3, bring in F3. Now I look at the poset. So I'm just looking now at a poset that contains just F1 and just F2. It's got one minimal element, F1. So I bring it in, right? And now I'm up to F1, F3. My partition poset has one remaining element, F2. I bring it in, and I'm up to the top. And notice, right, that if at the beginning I had decided to bring in F1 instead of F3, I would have this other path here, right? I would have brought in F1, then I would have had to bring in F3, and then F2. And so what this means is that the maximal chains in this path poset, or each path that goes from the root all the way up to the top, those are in one-to-one correspondence with the maximal path spaces. So if I want to know what maximal path spaces I have, I just construct this path poset, which, as we just saw, we can construct from my partition poset, and then it just tells me everything I want to know about my maximal path spaces and sort of how they intersect. Okay. So now we can move on to the question of, given a maximal path space, what's the shortest distance between the two trees within that path space? So I'll call it finding a local geodesic. Okay, so let's embed part of the tree space into R3. And so I'm going to represent my starting tree as a point in the positive orthant, my target tree as a point in the negative orthant. And I'm going to say that the orthants I'm allowed that are part of my path space are this one, and that one. So that means if I want a shortest path between those 2 points, it's got to go through that x3 axis, because that's the only way I can get between the allowed orthants. And so that means, right, it's got to lie in the plane that goes from the starting tree to the x3 axis, and then in the plane from the x3 axis to the target tree, which right now those 2 planes are bent. But I could unfold them, and I'm now in a lower dimensional space, right? I'm in R2. So I can find my coordinates in this new space by using Pythagoras' theorem. I should just point out that this is an isometric map, which means it's distance preserving. So if I find my other 2 coordinates, and then in my 2-dimensional space, I can easily find my geodesic, right? It's just a straight line between them because it goes through the allowed region in this case. And then I can map it back isometrically to my original tree space and get the geodesic there. So what we've done is we've mapped from tree space isometrically to a lower dimensional Euclidean space. Because what we do is for each group of edges we drop or add, that group is going to correspond to exactly 1 dimension, right? And that's how we go. So if stuff's grouped up, then we go to a lower dimensional space. So we can reformulate the problem as a Euclidean shortest path problem with obstacles, which is a computational geometry problem. And I should just point out it's known to be NP hard for n greater than 3 in the general case. And so we reformulated as a shortest path problem. So going from A, a point in the all positive orthant, to B, a point in the all negative orthant. And we're only allowed to go through certain orthants. Where the ith orthant that we're allowed to go through, the first I coordinates are negative or 0, and the remaining coordinates are positive or 0. And so in R2, this is what our picture looks like, and the orthant we're not allowed to go through is the obstacle. Okay, so our condition on this becomes, so in R2, for instance, we can easily see that if the slope of A to the origin is less than the slope of B to the origin, then we're going through the obstacle, and we can't use a straight line between A and B as our geodesic. But if that's not true, we have this condition, and the path from A to B, the straight line, is our shortest path. In higher dimensions, we can just project onto different pairs of coordinates and get a similar condition. So that what we want is that in higher dimensions, if the straight line between A and B is the shortest path, as in it doesn't go through any obstacles or non-allowed orthants, then, so this only occurs when, it's an if and only if really, when A over A1 over B1 is less than or equal to A2 over B2 is less than or equal to A3 over B3, etc. Or that we have this ascending ratio sequence. And then we know how to calculate the distance, right? It's just the Euclidean distance. So it's not likely the ratio sequence will be ascending. So if it's not, there's some first place where it's not ascending, where it's descending. So say from AI over BI to I plus 1 over BI plus 1. And we can show, which I won't do here because it's actually rather technical, that then the shortest path will go through the intersection of the I minus first, ith, and I plus first orthant. And what this means algorithmically is that we should just replace the ratios, these two ratios, with this ratio here. And so what we're doing is, if you remember that picture where I went from tree space to Euclidean space, you can actually reuse that same picture, except I'm going from Euclidean space down to one lower dimension Euclidean space. Okay. And so the algorithm is actually quite cute. So say we want to go from this path A to B. We construct a ratio sequence. First one's okay, okay. This one's out of order, so we apply our lemma, right? Just replace it with the new ratio. So we've dropped down from R5 to R4. We go through again, okay. Not okay, so we apply our lemma. So now we're dropping from R4 down to R3. And now we've got an ascending ratio sequence. So this means that in R3, our path, the straight line from A to B, goes through the allowed regions in R3. We can compute its distance, right, where first point's the numerators, the second point's given by the denominators. Compute our distance, and that's actually the distance, because we've been doing isometric maps, which are distance preserving, that's actually our distance between the 2 points in R5. And so this is a linear time algorithm. Okay, so now we put it all together. We have two trees. We construct a partition poset for them, construct a path poset for them. And I'm going to label my edges by, so the E is going to be the E that was dropped in order to bring in the F, right? So at each stage. And so it turns out we can do what we would hope we can do. And so there's a theorem backing this up, but I'm not going to try and state it here. And in that, let's just consider the ratios. So let's put some numbers on the problem. And consider the two paths that are going up to this node. We compute the distances for the sequences, basically just run that algorithm that combined ratios on the two sequences, see which gives the shortest distance out, and don't think about the geometric meaning here. There is one, but it's kind of complicated and not so instructive. And then whichever one's shorter, we're going to go with that one. And the other path, we say we can't go through. Okay. So now the next place where we have a choice of paths, right, is up here. And now we've only got two paths because this path was longer, so we can leave it out. So basically any longer path, any longer subpath in this poset is not going to be in my geodesic. So here, right, again, I can compute the two distances for these two sequences using that combining algorithm. In this case, that one, so the green one now is shorter. And so we keep it. And then finally, we go up to the last one. So from here, right, there's only one path now going into it. So we know so we know if we take this full ratio sequence and combine to get the distance, that's actually the local geodesic distance between these two trees in that. Sorry, that's a geodesic distance in that path space, but it's also, so it's a local geodesic distance, but it's also my global geodesic distance. And so we found it, and we're done. Unfortunately, the path poset can have an exponential number of nodes in the worst case, which means that the algorithm is in the worst case exponential in the number of leaves. In practice, this doesn't seem to be, it still seems to run quite fast because I did it on a set of trees, so 43 taxa of trees, and it was taking about 2.2 seconds per tree, which seems fairly reasonable. So that's it.
Zero property implies also that there is a barycenter for any finite set of points. Did you ever try to compute that for your
No. I mean, essentially, you have to be able to find a distance between them in order to compute it. And if you can't compute the distance quickly, then.
But you can.
Well, I'm still trying to get a polynomial time algorithm. So. Okay. Oh, yeah.